In the next 20 seconds, I will hand you a ruler for the cosmos. If the Milky Way is approximately 100,000 light-years across, how many fit across the observable universe? Hundreds, thousands, or millions? Here is the only measuring stick that works out here: light. We will use it carefully, step by step, and test our guesses against clear numbers. Before we sprint ahead, one clarification. The observable universe is simply the region we can measure because light has had time to reach us. It is not the whole of everything that might exist. This is the map we can actually test. Keep that in mind as we build scale from familiar to immense. So what does that actually mean? It means our map is centered here by necessity, while other observers would center theirs where they stand and still read the same laws. Light travels approximately 300,000 kilometers each second. In a year, that distance is 1 light year, nearly 10 trillion kilometers. Keep that in your pocket, because we will use it constantly for crossing space. We will convert time into distance anywhere light can travel, and compare structures on equal footing. Start in our neighborhood, the solar system. The moon is a little more than 1 light second away, which is why the Apollo radio calls had a slight delay. The sun is 8 light minutes from Earth, so the warmth on your face at noon began its journey a few minutes earlier. The outer planets sit hours of light travel time away, and the Kuiper belt extends farther still, taking many hours for a signal to cross. Already enormous, and yet this remains a speck inside a greater city of stars we call the Milky Way. What is a galaxy? In plain terms, it is a city of stars held by gravity, with gas and dust mixed through and dark matter as its unseen scaffolding. The Milky Way is a barred spiral. From inside, it appears as a hazy river across dark skies, the combined glow of billions of suns, too faint to pick out alone yet bright together. That river is our home address in the cosmos, and we read it edge on because we live inside one of its arms. Knowledge of that vantage point helps us interpret what we see without assuming we sit at the center. How wide is the Milky Way? Current estimates place its stellar disk at approximately 100,000 light-years across, with a thicker halo extending farther. Bank that number, we will stack it soon. A beam of light moving at nature's top speed would need approximately 100,000 years to go from one edge of the disk to the other. Stars drift on slow orbits, taking hundreds of millions of years to complete a lap, while our sun tugs its family along a path tens of thousands of light years from the center. Look toward the heart of the Milky Way, and visible light is blocked by dust. But infrared and radio views cut through and reveal a compact region anchored by a supermassive black hole. It weighs approximately 4 million times the sun's mass and acts like a gravitational keystone. Stars swarm around it on elongated paths, and gas occasionally spirals inward, heating up and shining before crossing the point of no return, where not even light can escape. Even so, most of the galaxy is quiet starlight and long arcs of orbiting material that set the pace of our celestial city. So how large is the universe compared to this? To feel the contrast, compare our galaxy with its immediate surroundings. The nearest large neighbor is the Andromeda galaxy, a spiral similar in scale, located approximately 2.5 million light-years away. How big does that actually look to your eye? Seen from Earth, Andromeda spans an area larger than the Moon, though most of it is faint without long exposures. That means its light left when early human ancestors were learning to use simple tools, and it has been crossing the dark ever since. The Milky Way and Andromeda belong to the local group, a small collection of big spirals and many dwarf galaxies bound together and spanning roughly 10 million light-years end to end. Gravity links these systems in a slow dance, and in a few billion years, the two giants will merge into a new, larger galaxy. That change unfolds at the tempo of cosmic seasons, rather than human calendars. Are we anywhere close to the universe's full scale? Not yet. Beyond the local group, other groups and clusters arrange themselves like neighborhoods and cities on a vast map. Where matter is dense, clusters of hundreds or thousands of galaxies form and glow with hot gas visible in X-rays. Where matter is sparse, giant voids stretch for hundreds of millions of light-years with only a few galaxies sprinkled through them. The pattern resembles a web, with bright nodes where many threads meet and dark gaps in between that go on across the survey volumes we have charted. This large-scale structure grew from tiny fluctuations in the early universe that gravity amplified over billions of years. We trace that growth with surveys mapping galaxy positions and with the faint afterglow of the hot early phase, the cosmic microwave background. That glow, a nearly uniform radio whisper from every direction, carries small temperature variations that act like fingerprints of the universe's initial conditions. From those fingerprints, scientists infer how much matter and energy the cosmos contains, and how fast space has expanded. Independent methods agree within their uncertainties, signaling a consistent picture while details continue to be refined. When we talk about the size of the universe, we must be careful with words. There is the part we can observe, limited by the time light has had to reach us since the hot early phase, and there is whatever may lie beyond that horizon. The observable region behaves like a sphere centered on us, because we receive the light here, while a distant observer would center their own sphere on themselves. The key idea is that the observable universe is not the whole universe. It is simply the accessible region for our measurements at this moment in cosmic time. Because space itself has stretched while light has been traveling, the current distance to the farthest galaxies we can see is larger than the naive light travel time would suggest. The radius of the observable universe is in the tens of billions of light years, and the diameter is roughly twice that. These figures come from standard cosmology tested with supernovae, background radiation, and galaxy surveys, and their precise values are refined as new measurements improve. The scale is enormous compared with any single galaxy. Stack the Milky Way against that scale and the contrast becomes clear. If our galaxy were a coin, the observable universe would be a country. The takeaway is that even a wide galaxy like ours occupies a minuscule patch of the measurable cosmic map we can actually chart. How do we know any of this when we cannot travel to those distances? The answer lies in careful use of light as a messenger. We build a distance ladder, starting with nearby objects whose distances we measure geometrically, then calibrate brighter standard candles visible farther away. We add methods based on the apparent size of known features and on how the expansion of space stretches light. Each method overlaps the next, tying the scale together and allowing cross-checks. Since the universe is expanding, distant galaxies are receding from us, and the light they emit is stretched to longer wavelengths. That shift to redder light is called redshift, and by measuring it, we estimate how much space has expanded while the light was en route. Combine redshift with general relativity and the observed distribution of matter, and you get a relationship between distance and recession speed on large scales. This is not motion through a static medium. Space itself is stretching between bound structures, in a way our equations describe and our data support. Scientists assign uncertainties to estimates and revise models when new evidence warrants, so numbers may shift as data improve. For our purposes, however, the plausible range still leads to the same conclusion. Our galaxy is huge by human standards, yet the observable universe is so much larger that plain numbers can feel like poetry. The contrast is not meant to make us feel small, but to give us an honest scale against which wonder can grow without distortion. Are we anywhere close to the final count? We are ready to compute. We have built the only ruler that works out here and pinned our galaxy onto the map we can actually observe. Next, we will answer the question you came for. Exactly how many Milky Ways fit across the observable universe, and what hidden assumption can flip the number on its head. We will show the arithmetic so you can run it yourself, and then stress test the result against the ways astronomers define distance. We are ready to compute, so let us set our terms clearly. The Milky Way stellar disk is approximately 100,000 light-years across, which we will treat as a working diameter. The observable universe spans approximately 92 billion light-years in diameter, a value that reflects the stretching of space while light traveled. Headline: approximately 920,000 across with the moving ruler. Alternatively, approximately 276,000 with the light travel ruler. Here width means our working diameter for the Milky Way. Place those two numbers side by side, and the scale begins to reveal itself without ornament. How many Milky Ways fit across that approximately 92 billion light-year span? Divide 92 billion by 100,000, keeping the units consistent and the round numbers honest. The result is approximately 920,000, meaning nearly 1 million Milky Way widths laid edge to edge would just reach across the observable universe. That is the simple count along a straight line, not an area or volume tiling, only a one-dimensional comparison to anchor intuition. Why call out a hidden assumption? Because our answer depends on which cosmic distance we choose to compare. If we had used light travel time alone, 13.8 billion years each way for a naive radius, we might have estimated a diameter around approximately 27.6 billion light-years. That would give approximately 276,000 Milky Way widths across, a smaller figure that undercounts because it ignores how space has expanded while the light was en route. It is about choosing the ruler that fits the question. This is not motion through a static medium. It is expansion deciding how we measure. Light travel time answers how long has the light been on the road, while moving distance answers how far apart are those points right now. For comparing sizes today, the Milky Way now versus the observable universe now, the moving ruler is the correct match. If instead we asked how many Milky Ways the earliest light has crossed since emission, we would choose the light travel ruler and live with the smaller number for that specific story. Let us pressure test our input for the Milky Way itself. The stellar disk is approximately 100,000 light-years, but the faint stellar halo and dark matter halo extend much farther. If you used approximately 150,000 light-years as a generous stellar diameter, the across the universe count would drop to approximately 613,000. If you insisted on a compact star-forming disk closer to approximately 80,000 light-years, the count would rise to approximately 1.15 million. The headline stays within hundreds of thousands either way, depending on the precise edge you choose and the distance definition you pair it with. A quick note on packing versus lining up. Our calculation is a one-dimensional lineup across the diameter, not a two-dimensional tiling of a surface, and not a three-dimensional filling of volume. Those are different problems with different geometries and would produce much larger counts. We stay with the across-the-sky question because that is what "how many fit across" naturally implies in everyday language, and it keeps the analogy clean. For listeners, does cosmic curvature change the picture? In the standard model with nearly flat geometry on large scales, straight-line distance across the observable region behaves as we have described. Local curvature near massive clusters can lens light and bend apparent positions, but it does not shrink the comoving diameter of the whole observable sphere in a way that changes our order of magnitude. The uncertainties in cosmological parameters shift the approximately 92 billion light-year number by only a few percent. Our answer remains stable under those variations and honest about its inputs. There is another subtlety worth naming because it prevents confusion later. Astronomers use several distance definitions beyond comoving and light travel. Angular diameter distance relates a known physical size to the angle it spans on the sky, and luminosity distance relates a known brightness to the observed dimness after the light has spread out and redshifted. At low redshift, these measures are similar, but at high redshift, angular diameter distance behaves non-intuitively. Objects can appear larger again as redshift increases. That oddity is built into the mathematics of expansion and does not contradict our lineup comparison across today's diameter. Let us sanity check with a back of the envelope that stays faithful to the big picture. Treat the observable universe as a sphere of diameter approximately 92 billion light-years. Place a ruler of approximately 100,000 light-years along a straight line through the center. You can place approximately 920,000 such rulers end to end across the diameter. For the circumference, multiply by pi, and for a great circle you would find approximately 2.89 million Milky Way widths around. Still a one-dimensional measure, but one that shows how choice of path affects the count, while keeping the same inputs. How sensitive is the count to the exact cosmological numbers? Changes in the Hubble parameter within current estimates nudge comoving distances by a few percent for a fixed redshift. The matter and dark energy densities play similar roles in setting the growth history and the translation between redshift and distance. Across reasonable values, the approximately 92 billion light-year diameter slides slightly, but the headline remains. Hundreds of thousands to about 1 million Milky Way widths across. That stability is useful because it means the comparison is not a house of cards, resting on one fragile input. Another useful cross-check is to think in times rather than distances, then translate. The age of the universe is about 13.8 billion years, but because space expanded during the journey, the most distant galaxies we can see are now much farther than 13.8 billion light-years away. That is the same logic we already used, just from the time side. It explains why people sometimes quote a smaller number when they speak in terms of how long the light has been traveling, and a larger number when they speak in terms of how far apart those places are now. Naming which view you are using keeps conversations clear. It is worth stating what this comparison does not claim. Lining up Milky Ways across the observable universe does not say anything about how galaxies are actually arranged, nor does it suggest that real galaxies could be packed without gaps. Large-scale structure is clumpy, with filaments, clusters, and voids shaping where galaxies live. Our count uses a consistent diameter to compare two scales and nothing more. It is a visualization aid that helps the mind hold two sizes in view at once, without overpromising. Now gather the versions in one place so you can choose based on the ruler. With an approximately 92 billion light-year comoving diameter and an approximately 100,000 light-year Milky Way, the across the diameter count is approximately 920,000. With an approximately 27.6 billion light-year travel time diameter, the count is approximately 276,000. Shift the Milky Way's working diameter to approximately 80,000 or approximately 150,000 light-years, and the counts adjust to approximately 1.15 million or approximately 613,000 respectively. State the ruler. State the Milky Way edge. Perform the same division, and you will reproduce the result every time. So the crisp version is this. Across the observable universe today, you could place approximately 920,000 Milky Way diameters end to end, using an approximately 100,000 light-year Milky Way and an approximately 92 billion light-year observable diameter. If you insist on the light travel ruler, the answer becomes approximately 276,000, and if you adjust the Milky Way's edge, the count slides within the hundreds of thousands. The choice of ruler is the lever. Name it out loud, and the number makes sense, rather than floating free of context. Next, we will open the box behind those inputs and show how astronomers build the distance ladder that feeds them. We will begin with parallax, the geometric shift of nearby stars as Earth orbits the Sun. Then step to standard candles like Cepheid variables and type Ea supernovae. We will connect those to redshift-based methods and to features imprinted on the large-scale distribution of galaxies. At each rung, you will hear exactly where uncertainties enter and see how overlapping techniques allow cross-checks that keep the numbers honest and reproducible. We have answered the headline and highlighted the assumption that flips the count. The arithmetic is transparent, the inputs are named, and the outcome is stable against small shifts in the parameters. In the next part, we will walk one rung at a time up the distance ladder and show how measurement, calibration, and overlap make the scale trustworthy. That way, you can carry the method, not just the number, into any future conversation about cosmic size. We have the headline comparison, so now we climb the distance ladder that makes those inputs trustworthy. The goal is simple and careful. Show how nearby yardsticks anchor farther ones until we can read distances across deep time. We begin with parallax, a geometric shift that requires nothing more exotic than motion and angles. When Earth moves around the Sun, nearby stars appear to slide slightly against the more distant background, and that slide gives us a baseline in pure geometry. Measure the angle of that apparent shift, and you can solve for distance the same way surveyors measure the width of a river without crossing it. Parallax is defined in plain words as half the apparent shift of a nearby star when observed 6 months apart, because Earth has moved to the opposite side of its orbit. The larger the shift, the closer the star. For very close stars, that angle is measurable in fractions of an arcsecond, a tiny slice of a circle. Space missions that specialize in astrometry, the careful mapping of star positions, have pushed this technique to extraordinary precision. With a stable platform above Earth's shimmering air and a long-time baseline, parallax distances reach thousands of light-years with direct geometric confidence. A parallax of 1 arcsecond defines 1 parsec by construction, about 3.26 light-years. Parallax alone does not take us to other galaxies, but it does something equally important. It calibrates the intrinsic brightness of certain nearby stars, whose light can be seen much farther away. If you know how bright a kind of star truly is, and you measure how bright it appears to us, you can calculate how far away it must be. The difference between intrinsic brightness and apparent brightness is the dimming that distance imposes, spread over the growing sphere that light occupies as it travels. This move from geometry to photometry is the first long stride on the ladder. One especially useful type of standard candle is the Cepheid variable star. These are pulsating stars whose brightness rises and falls in a regular rhythm. The period of the pulsation is tied to the star's true luminosity through a relation discovered by careful observation and then grounded with physical models. Read the period to infer luminosity. Compare the inferred luminosity to the observed dimness. The result is distance. Because Cepheids are bright, we can see them in nearby galaxies, and that extends the reach of the ladder far beyond parallax alone. To keep the chain honest, astronomers build overlap between rungs. Some Cepheids are close enough for parallax, so their inferred distances from brightness can be directly cross-checked against geometry. That overlap lets us refine the relation between period and luminosity, reduce systematic errors, and carry the calibration outward. The same philosophy repeats at the next rung, where we use even brighter events, type Ia supernovae. These are stellar explosions with a relatively uniform peak brightness after we apply well-understood corrections based on how their light curves rise and fade. Type Ia supernovae are bright enough to be seen across a large fraction of the observable universe. When we observe one in a distant galaxy, we can estimate its true peak luminosity from the shape of its light curve and then compare to its observed brightness. That gives a distance, and the redshift of the host galaxy gives a measure of how much the universe has stretched during the light's journey. Plot many such supernovae over a wide range of redshifts, and you read the recent expansion history in the curve they trace. This rung does not replace Cepheids. It is connected to them. Some galaxies host both, which keeps the calibration tied together. Alongside supernovae, there is another ruler embedded in the large-scale clustering of galaxies, the baryon acoustic oscillation scale, often shortened in speech to the acoustic scale. In the early hot universe, pressure waves rippled through the plasma of photons and matter, leaving a preferred separation scale imprinted in the way galaxies are distributed today. When we map millions of galaxies and compute their statistical clustering, a subtle bump appears at a separation that acts like a standard ruler. That preferred separation is the acoustic scale. The physical size of that ruler is set by early universe physics and cross-checked with the cosmic microwave background. So measuring its apparent size at different redshifts tells us distances. The microwave background itself is the oldest light we can see directly, the afterglow from when the hot plasma cooled enough for neutral atoms to form and photons to travel freely. It is nearly uniform, but not perfectly so. Tiny temperature variations across the sky encode information about the composition and geometry of the universe. By analyzing how those variations change with angular scale, astronomers infer the basic parameters that set distances over cosmic time. The background's message is statistical and subtle, but it threads through the latter, providing boundary conditions that every other measurement must respect. Because the latter uses different kinds of data, it matters that each rung overlaps with neighbors. Overlap allows independent checks for hidden biases and systematic errors. For example, if dust in a galaxy dims a supernova more than expected, the inferred distance would be too large. But if that galaxy also contains Cepheids, or sits in a survey where the acoustic scale has been measured, discrepancies surface. Teams deliberately look for such mismatches because discovering and correcting them tightens the entire structure rather than undermines it. The strength comes from redundancy and from the willingness to revise when evidence demands it. There is an idea called the distance modulus that packages the brightness information in a convenient way. It is simply the difference between the apparent magnitude and the absolute magnitude of an object, and it maps logarithmic brightness ratios into linear steps. In everyday words, it is a way to say how many steps away an object sits on a brightness staircase. A change of 5 magnitudes corresponds to a factor of 100 in brightness. A change of 5 magnitudes corresponds to a factor of 10 in distance for the same kind of source. This mathematical convenience helps keep the arithmetic clean when combining candles of different types. Parallax, Cepheids, supernovae, acoustic rulers, and the microwave background are the backbone. Additional techniques weave through them. Surface brightness fluctuations in nearby galaxies provide distances by measuring how pixel-to-pixel variations change with distance. The tip of the red giant branch, a well-defined feature in the color brightness diagram of old stellar populations, acts as another candle in the same spirit as Cepheids. Gravitational lensing time delays add a geometric method at larger scales. When a variable source is multiply-imaged by a foreground mass, differences in light path length and gravitational potential produce measurable time lags that encode distance. Every rung brings its own sources of uncertainty. For parallax, it is instrumental precision and the stability of the reference frame over years. For Cepheids, it includes metallicity, the chemical composition that can shift the period-luminosity relation. For supernovae, it is the uniformity of the population and how well dust and viewing angles are modeled. For acoustic rulers, it is the fidelity of the galaxy map and the modeling that connects galaxy clustering to the underlying matter distribution. Good practice is to quote not only a best estimate, but an uncertainty, and to check that different methods point to the same scale within those bounds. At this point, it is fair to ask a healthy question. If two well-regarded methods produce slightly different values for a key parameter, what should we conclude? The scientific answer is not to pick a favorite and ignore the other. It is to look for subtle systematics, to test with fresh data, and to add new independent methods. In the last few years, this disciplined approach has refined the numbers without changing the broad picture that matters for our comparison. The observable diameter remains vastly larger than a single galaxy's width, and the count of Milky Way diameters across remains in the hundreds of thousands to about 1 million, depending on the chosen edge and ruler. Now let us make the latter tangible with a narrative walk. Imagine we start with a parallax target, a nearby star whose position we track over several years. The tiny annual wobble yields a distance in light years that is as direct as any measurement in astronomy. In that same region, we find a Cepheid, measure its pulsation period, and calibrate its intrinsic brightness using the parallax ladder. With that calibration, we can measure distances to a small host galaxy where another Cepheid lives, far beyond parallax reach. In that host, we catch a type, Ia Supernova, and read its light curve, using the Cepheid-based calibration to peg its peak luminosity. With that supernova distance and the host galaxy's redshift, we place a point on the expansion history plot. Repeat this process for many hosts across the sky, and you sketch the curve that describes how space has stretched over time. Overlay on that curve the distances inferred from the acoustic scale at matching redshifts, and check for agreement. Both methods tie back to the microwave background's parameters, which provide the initial conditions and overall geometry. The match is never perfect in a simple sense, because each method has uncertainties and its own window on the cosmos, but the overlaps show a coherent story. This overlapping web of evidence is the reason we can speak confidently about the size of the observable universe today without resorting to sensationalism. We are not leaning on a single technique or a single instrument. We are leaning on multiple, independent, cross-checked threads that converge on the same order of magnitude for distances at every step. Even where active debates remain over the exact values of certain parameters, the differences shift final distances by only a few percent at the scales that matter for our comparison. That shifts the count by a similar percentage, not by orders of magnitude. It is useful to mention one more geometric insight tied to expansion. In an expanding universe, distance is not a static concept. Proper distance means separation at a chosen moment in cosmic time, while comoving distance factors out the expansion, so that the grid on which galaxies sit stays fixed. Angular diameter distance tells us how a known size projects onto the sky, and luminosity distance tells us how brightness fades with both distance and redshift. These ideas sound abstract, but they do practical work. Choosing the right one for the question is half the battle. For our count across the observable universe today, proper distance at the present epoch, often expressed as comoving distance in this context, is the apt choice. It matches the notion of the Milky Way's diameter as it is now, not as it was when light left some far-off galaxy billions of years ago. When you hear someone quote a smaller diameter by using light travel time alone, you can now translate between the two. You know which ruler they picked and how to compare their number to the count we used earlier. There is a final check that feels almost philosophical but remains practical. Astronomy depends on light as a messenger, and messengers can be tricked by intervening matter. Dust absorbs and reddens, gas scatters, and gravity bends. All of these effects are measured, modeled, and folded into the methods above. The redundancies mean that if one path underestimates a correction, another path likely reveals the discrepancy. This is how the field avoids the trap of a beautiful but fragile explanation. It prefers a sturdy explanation, one that creaks under testing without collapsing. Step back now and look at what the latter accomplishes. It lets us start from a geometric shift measured over a human year and end with distances that span billions of light years. It does so in stages, each stage checked by neighbors, all of them tied to the same physical principles of light and gravity. The result is not only a number, but a method. Numbers can be misremembered or updated, but a clear method can be repeated, taught, and adapted. That is why we spent time here, so the size comparison rests on a foundation you can examine. We will close this part with a compact recap. Geometry anchors the first steps with parallax. Standard candles extend the reach with Cepheids and Supernovae, tied back to geometry through overlap. Statistical rulers in galaxy clustering and the ancient light of the microwave background weave in from the other end of time and scale. Together they fix the map well enough that saying approximately 920,000 Milky Way widths across the observable universe is not a guess. It is a carefully translated statement, built from many small, testable steps. How does the count shift if we move the Milky Way's edge by 10%? We have the ladder and the headline counts. Now we will work through explicit, transparent examples that you can repeat on a notepad. We will compute the across the diameter count with two distance conventions, and then move the edge of the Milky Way to see how the result shifts. Each example stands alone, but together they show why naming the ruler out loud keeps conversations clear. Example 1. Moving diameter today. Use an observable universe diameter of approximately 92 billion light-years and a Milky Way diameter of approximately 100,000 light-years. Divide 92 billion by 100,000. The quotient is approximately 920,000. Read that as approximately 920,000 Milky Way widths, placed end-to-end, would span today's observable diameter along a straight line, a one-dimensional comparison across the diameter, not an area or volume fill. Here, width means the Milky Way's working diameter. Example 2. Light travel time diameter. Use a diameter of approximately 27.6 billion light-years, derived from approximately 13.8 billion years of light travel time each way for a naive radius. Divide 27.6 billion by 100,000. The quotient is approximately 276,000. Read that as, using the travel time ruler, you get approximately 276,000 widths across the current observable diameter. Example 3. Vary the Milky Way edge upward. Keep the moving observable diameter at approximately 92 billion light-years, but use a working Milky Way diameter of approximately 150,000 light-years to reflect a more generous stellar disk. Divide 92 billion by 150,000. The quotient is approximately 613,000. The headline remains in the hundreds of thousands. Example 4. Vary the Milky Way edge downward. Keep the moving observable diameter at approximately 92 billion light-years, but use approximately 80,000 light-years for a compact star-forming disk. Divide 92 billion by 80,000. The quotient is approximately 1.15 million. Example 5. Circumference instead of diameter. Stay with the comoving observable diameter of approximately 92 billion light-years and treat the circumference as pi times the diameter. Multiply 92 billion by pi to get approximately 289 billion light-years. Divide by 100,000 and you find approximately 2.89 million Milky Way widths around a great circle. The path changed, not the inputs. Example 6. Sensitivity to cosmological parameters. Suppose the best fit diameter drifts by a few percent as measurements update within their uncertainties. A 3% change in approximately 92 billion light-years is approximately 2.76 billion light-years. Divide that change by 100,000, and the count shifts by approximately 27,600 in either direction. The order of magnitude remains unchanged, which is why the headline is stable. Example 7. Angle to distance translation in plain words. Imagine a nearby spiral galaxy with a star-forming region known to be approximately 1,000 light-years across from resolved mapping. On the sky, that region spans an angle that you can measure with a ruler on the image. Angular diameter distance is the present-day separation that makes the known size match the observed angle. If the angle halves while the known size stays fixed, the inferred distance doubles because the same yardsticks project smaller. Example 8. Brightness to distance translation in plain words. Take a standard candle, such as a calibrated type Ia supernova. Its intrinsic brightness is known to within quoted uncertainties after we account for the shape of its light curve. Luminosity distance is the separation that makes the intrinsic brightness match the observed dimness once redshift and spectral band shifts are considered. If two otherwise similar events differ by 5 magnitudes in observed brightness, the more distant event is approximately 10 times farther away. That rule of thumb turns logs into steps you can count. Example 9. A short redshift ladder. Consider 3 host galaxies with modest redshifts, 1/10, 3/10, and 6/10. Distances based on comoving conventions increase nonlinearly as you rise through this ladder, because expansion history shapes the translation between redshift and distance. A simple way to speak about this without equations is to say that each rung stretches the grid beneath the light while it travels. The farther back you look, the more that stretch matters for the count across the diameter. Example 10. Borg nu periodicane 9 period u bit. The observable diameter has a 2% uncertainty, and the Milky Way working diameter has a 5% uncertainty. Then the ratio inherits approximately 5.4% uncertainty added in quadrature. That means the across the diameter count moves by only several percent, not by factors of 2. The method is resilient because both numerator and denominator are well constrained by overlapping measurements. Changing either within reasonable limits nudges the count rather than topples it. Now let us turn examples into a pocket method. Step 1. Name the ruler. Comoving diameter today, or travel time diameter. Step 2. Write down the Milky Way working diameter you will use. Step 3. Divide. Step 4. Name the path and state your answer as across the diameter unless you explicitly chose a different path, such as the circumference. Step 5. Disclose any assumption about the Milky Way's edge in one short phrase. This is the checklist that keeps the conversation honest and comparable. From telescope to number, a compact pipeline you can picture. A telescope collects light on a detector and creates images where each pixel registers counts. Those counts are corrected for dark current, bias, flat fielding response, and sky subtraction, so that instrumental quirks do not masquerade as sky signals. Calibrated stars with known brightness tie the image to a standard scale, and atmospheric extinction is removed with measured coefficients. A spectrum or a set of narrow-band images yields a redshift for the host galaxy. With that redshift in hand, a distance is inferred using the agreed cosmological parameters, and one of the distance definitions we named earlier. The source brightness is corrected for dust and shifted to the rest frame, and the final pair, distance and redshift, becomes a point on a plot. Why that point matters. A single, well-measured point is a small thing, but many points create the curve of the recent expansion and anchor the cross-checks we discussed in the ladder. Your count across the diameter is not inserted into that plot, yet it sits on the same foundation because the diameters we used were derived from the same network of data. That is why examples and pocket methods are more than tricks. They are distillations of a longer chain that begins with photons on a sensor and ends with distances voiced in clear words, without sensationalism. Frequently asked angle 1. What lies beyond the observable region? The honest answer is that we do not have direct access to it, so we do not count it in this comparison. The observable boundary is set by light's travel and by expansion, and that boundary grows with time as more light arrives. In other words, the horizon recedes as the universe ages, so future observers will have more of the map to measure. Our method adapts by plugging in the updated diameter and repeating the same division with the Milky Way width you choose. Frequently asked angle 2. Do gravitational lenses change the headline? Gravitational lensing can magnify and distort individual sources, and strong lenses can even create multiple images with time delays. Those effects are folded into the distance ladder rungs that inform the diameter we used, but they do not rescind the across the diameter count itself. A lens bends paths locally, while the comoving diameter describes a global separation today. The count is a large-scale statement that survives small-scale wrinkles, introduced by mass along the line of sight. Frequently asked angle 3. Why not tile the observable sphere with Milky Ways to get a more impressive number? Tiling an area or filling a volume is a different question with different geometry. Across the diameter uses one-dimensional intuition that maps to how we look across the sky and compare end to end. Area tiling would require curvature-aware packing rules and would produce a larger figure that is less directly felt by a listener. Staying with the across-the-diameter phrasing keeps the comparison intuitive and avoids false precision. Hands on drill, run the numbers with your own inputs. Choose a Milky Way edge that you like, compact star-forming disk, generous stellar disk, or an even broader definition if you are testing a scenario. Choose a ruler, comoving today, or travel time. Perform the division and say the answer with its ruler named. If you want a circumference answer, Multiply the diameter by pi before you divide. Finally, speak your assumptions in one short line so another person can reproduce your result without guessing. A visual imagination aid that respects the numbers. Picture a line across the sky from one horizon to the other. On that line, lay down a transparent strip labeled Milky Way width. Copy and paste that strip again and again while counting quietly. When you reach approximately 920,000 copies with a moving ruler, you have a mental representation of the across the diameter count. If you prefer the travel time ruler, stop at approximately 276,000. This picture is crude yet helpful because it ties the number to a tangible act. Edge cases worth naming, so we are not surprised by them. If someone chooses a Milky Way width defined by a faint outer stellar halo or by a dark matter halo edge, they will produce a smaller count because the denominator is larger. If someone chooses a narrow width defined by the bright star forming ring, they will produce a larger count because the denominator is smaller. Both are logically consistent, which is why we always demand that the edge be stated in the same breath as the answer. The same logic applies to the diameter. State whether it is moving today or travel time, and the conversation stays honest. A micro tour of units that keeps narration smooth. When you hear billion and thousand, remember that the words carry the powers of 10 that would otherwise clog a sentence with zeros. Light year is a distance, not a time, defined by how far light travels in 1 year. Moving distance is a present-day separation that factors out the expansion so that the coordinate grid does not flow under your feet as you compare sizes. Travel time distance is the path length the light would have covered if space had not been stretching beneath it, which is why it gives a smaller figure for the same pair of points. Worked micro example with a different galaxy as the local yardstick. Suppose you prefer to think in terms of the Andromeda galaxy rather than the Milky Way. If you take a characteristic Andromeda diameter of approximately 220,000 light-years based on its extended disk, divide the moving observable diameter by that value, 92 billion, divided by 220,000 yields, approximately 418,000. The message is unchanged. The observable diameter dwarfs any single galaxy and sits comfortably in the hundreds of thousands when counted in familiar widths. Another micro example that stresses the path we pick. Instead of across the diameter, take a diagonal chord that is shorter than a great circle by a factor set by the angle it spans. If you choose a chord that is half the diameter, you would obviously need half as many Milky Way widths. The rule is simply that path length controls the count once your width is fixed. We prefer the diameter path because it is the cleanest end-to-end statement and because listeners picture it easily when they imagine a line across the sky. What changes in a far future where the observable region is larger? The method does not change at all. Future observers will plug in a larger diameter set by additional light that has reached them and by the continued evolution of expansion. Their counts will be larger in proportion to the new diameter. Our present count is a snapshot anchored to today's inputs, which is why we explicitly say today when we name the moving ruler. Saying when the ruler applies is part of being precise. A final synthesis to close this worked section. You now have two parallel tracks in your hands. A narrative track that explains rulers, edges, and paths in clear language, and a calculation track that divides two numbers after spelling them out. The tracks reinforce each other and reduce the chance of confusion. They also model a habit that travels well beyond this topic. Name your definitions, show your arithmetic, and quote an uncertainty when you can. With those habits, scale comparisons turn from loose metaphors into testable statements that invite curiosity rather than arguments. We have turned the headline into many worked steps you can repeat and adapt. You have seen how the count depends on the ruler, on the path, and on the chosen edge for the Milky Way. You have a checklist and a pipeline in mind that connect pictures on a detector to points on a distance plot, and from there to the diameters we used. In the next part, we will take on two more angles: what happens to structures during a future Milky Way and Andromeda merger, and how distance choices appear in a real observation pipeline from raw images to a plotted point on a distance redshift diagram. The aim is steady: careful claims, visible methods, and room for better data as they arrive. We now bring two final angles into focus: what happens to structure during the future Milky Way and Andromeda merger, and how distance choices appear inside a practical observation pipeline from raw images to a plotted point. The goal is steady: careful claims with numbers in words, one ruler named at a time, and no sensationalism. First, the future merger. The Milky Way and the Andromeda galaxy are on trajectories that will likely bring them together in several billion years. Their stars are so sparsely spaced that few will collide directly, but their mutual gravity will tug on orbits, fling some stars to wide paths, and draw many onto new settled orbits in a remade galaxy. Gas clouds will compress in places, triggering new star formation, while other regions will be stirred and heated so that star formation slows. After the encounter and its aftershocks, the system will settle into a larger, more spheroidal or lenticular remnant with a different light profile than today's two spirals. How do we picture that process without overdrama? Think of long tidal bridges and tails that arc between the galaxies, drawn out by gravity as the two disks pass. Those bridges carry clusters and clouds into the intergalactic space between the partners, where they fall back later along new trajectories. Tidal tails curve like ribbons, and within them we sometimes see compact knots, where gas has pooled and formed new stars. In simulations, the first pass twists the disks and throws loops outward. The second pass tightens the coupling. Repeated swings drain orbital energy until the cores sink together. At the centers lie supermassive black holes. Each weighs millions of solar masses in the present-day Milky Way and Andromeda. During the merger, dynamical friction against the surrounding stars and gas drags the central black holes toward each other. They form a bound pair that hardens over time as it slings nearby stars away. Eventually, gravitational waves carry the last energy and angular momentum, and the pair coalesces into a single heavier black hole. None of this changes our across the diameter count today, because the count is a ratio of two present-day sizes: the present-day observable diameter divided by the present-day Milky Way working diameter. It helps define what the local yardstick would be in the far future. The light distribution of the remnant, not the spiral width we use now. Does a merger change our across the diameter count? In spirit, no, because the count is a ratio of two present-day sizes, not a prediction of future geometry. Our comparison asks how many Milky Way widths, width means our working diameter for the Milky Way, fit across the observable diameter today. In several billion years, the local working width would belong to the merged remnant rather than to today's Milky Way. And the observable diameter would also be larger because more light will have arrived. The method would not change. Name the ruler, name the local width, divide, and state the path. The input values would change together over time, which is why the headline is always anchored to a date. One practical curiosity follows from the merger scenario. Even though stars rarely hit each other, close passes and shifting tidal fields can scramble the outer halos and fling streams of stars across vast distances. Those streams become tracers that map the gravitational potential of the remnant and its environment. In the long view, such debris is a laboratory for measuring mass distributions because the paths of the streams encode the total pull from visible matter and from dark matter. The merged galaxy's working diameter will be defined by a new light distribution, and observers will adopt a clear edge definition so that counts remain comparable. Another subtle point is angular momentum redistribution. Disk stars orbit in an organized rotation. During an encounter, torque geeks exchange angular momentum between stars, gas, and the combined halo. Some stars gain and move to wider, slower orbits. Others lose and sink inward. Gas can lose angular momentum quickly because it can shock and radiate, so it spirals inward and feeds star formation near the center, while leaving outer regions depleted. This is one way mergers build central bulges. Again, our counting method is unaffected in principle because the method only demands that we state which working diameter we are using when we divide. Now to the observation pipeline in practice. Begin with planning and calibration frames so that each raw exposure can be turned into images with bias subtraction, dark current correction, flat fielding, and sky subtraction applied, with known orientation and plate scale. Take science exposures that include calibration stars, whose apparent brightness is well measured and tied to a standard system. Extract spectra for redshifts, or measure narrowband features that serve the same purpose. Clean the catalog of artifacts and blend issues so that each source's light is measured consistently. Then propagate uncertainties from photon counts and calibration terms so that the final numbers carry honest error bars. A modern pipeline proceeds in stages. First comes instrument signature removal. Bias subtraction removes the fixed offset of the detector. Dark current correction removes thermally generated counts. Flat fielding corrects pixel-to-pixel sensitivity differences. Sky subtraction removes the bright and varying foreground of the atmosphere and the instrument. Astrometric calibration maps image pixels to sky coordinates so that sources align across multiple exposures. Photometric calibration ties instrumental counts to a physical brightness scale, using reference stars with known fluxes. Next comes image combination. Multiple short exposures of the same field can be registered and coded to improve signal-to-noise. Point spread function modeling captures how the atmosphere and optics blur a point source, which allows consistent measurements of blended or faint sources. Source detection finds candidates above the noise, and deblending separates neighbors whose light overlaps. Aperture corrections or model-based fits recover total fluxes. Color measurements are made in matched apertures, so that ratios between filters are not biased by different seeing conditions. If spectra are available, redshifts are measured from line positions. If spectra are not available, photometric redshifts estimate distance using the way a galaxy's color changes with redshift and with galaxy type. In both cases, a redshift becomes an input to distance once a cosmology is chosen, and the chosen distance definition must be named. If the question is a count across the observable diameter today, moving distance is the match today. If the question is how long the light has been traveling today, travel time is the match. If the question is how large a feature appears today, angular diameter distance is the match. If the question is how bright a candle should appear today, luminosity distance is the match. Now follow one source from pixel to plotted point. An exposure records a faint transient in a distant galaxy. Calibration frames remove instrument signatures. Sky subtraction flattens the background. Reference star fields set the brightness scale. A follow-up spectrum measures the redshift. If the transient is a type Ia supernova with a well-sampled light curve, the curve shape yields an intrinsic peak luminosity after standard corrections. Comparing that intrinsic luminosity to the observed dimness gives a distance on the luminosity distance ruler. Pairing that distance with the measured redshift places a point on the expansion history plot. Even in this clean narrative, real analysis protects against pitfalls. Dust can redden and dim, so multi-band observations are used to solve for and remove extinction. Host galaxy light can blend with the transient, so image differencing isolates the changing source. Misclassifying a transient would bias the inferred intrinsic luminosity, so classification models and spectroscopic checks are used. Pipeline steps are cross-checked with independent codes or simple verification calculations, so that hidden assumptions do not slip through unexamined. A short coda on language, because methodology depends on clarity. Width, diameter, radius, separation, and path length are not interchangeable words in this topic. Width is our working diameter for a galaxy-sized yardstick. Diameter is an across-the-center chord of a sphere or disk. Radius is the distance from center to edge. Separation is any distance between 2 points that you can state with a chosen ruler. Path length is the distance along a chosen route, a diameter, a circumference, or another specified chord. Name the word that matches the path you pick. Let us add a worked microset focused on edge definitions, because that choice often hides under the carpet. Suppose an observer defines the Milky Way edge by the radius where the stellar surface brightness falls below a specified threshold. Another observer defines the edge by the radius that encloses a set fraction of the total light. These are both reasonable, but they give different diameters. When those observers divide the observable diameter by their working widths, they will report different counts that are both internally consistent. This is why we ask for the edge definition to be stated in the same breath as the number. A parallel microset handles diameter choices. One team quotes a moving diameter today. Another quotes a diameter derived from light travel time. A third uses a path around a great circle rather than across the diameter. None is wrong, but each answers a slightly different question. The fix is simple and durable. Name the ruler, name the path, and speak the epoch. That single sentence makes 3 numbers comparable because the method behind them is exposed rather than implied. Return briefly to the merger and ask how observers in that future would speak. They would define a working width for the remnant, perhaps the diameter, enclosing a chosen fraction of light, and they would insert the larger observable diameter of their epoch. The division would give a different number, but the method would be the same and therefore comparable. What about environments beyond the local group? Galaxy clusters merge too, and on those scales hot gas in the intracluster medium carries much of the baryonic mass. X-rays trace that gas, while gravitational lensing maps the total mass directly, including dark matter. Both tools are part of the same distance network that feeds our diameters. Counts across the diameter speak to scale, not to packing or to mass. But the consistency of methods from stars to clusters builds trust in the background numbers we use for the comparison. We can also connect back to large-scale structure without leaving the method behind. The acoustic scale we named earlier shows up as a preferred galaxy separation in clustering statistics. That preferred separation is the acoustic scale. That scale is measured at many redshifts and translated into distances using the same cosmological parameters that help set the observable diameter. When independent roots agree within quoted uncertainties, we say the map is consistent. When they disagree, we search for systematics and refine the measurements until the story tightens. Either outcome teaches and improves the foundation under our count. A final pipeline vignette turns numbers into a picture you can imagine. After calibration and measurement, a set of supernova distances and redshifts are plotted on a diagram. A smooth curve that passes through those points represents the best fit expansion history within a chosen model. The observable diameter we use is one translation of that history into a present-day separation. You could change certain parameters within their uncertainties and watch the curve shift slightly. The present-day diameter would slide by a few percent, and the count would slide with it by a similar fraction, not by an order of magnitude. Before we close, gather the key phrases you can say out loud as a compact checklist. Name the ruler. Name the path. Name the epoch. Name the edge. Show the division. Quote an uncertainty if you can. Invite the listener to repeat the arithmetic. Those habits make scale comparisons reproducible and turn a large number from a stunt into a teachable statement. Bring both angles back to our central comparison. A far future merger will replace the local yardstick with a new one, defined by the remnant, and the observable diameter will have grown. The same division will produce a new count whose meaning is unchanged. A present-day pipeline applies rulers carefully to turn photons into distances and to anchor the diameters we used. Both paths reinforce the same habit. Define your terms, choose your ruler, show your arithmetic, and speak your uncertainty. That habit lets the number teach without overreach. Stand with me at the edge of thought and let scale arrive slowly. First, the human step. A breath, a heartbeat, a glance up at night where a narrow river of light threads the dark. Then the galactic step, the Milky Way spread as a hazy band, 100 billion suns braided into lanes and knots that circle for hundreds of millions of years. Finally, the horizon step, the observable sphere, a present-day diameter so large that words bend under it, and yet it is still only the part we can test, because light has reached us. Hold those 3 steps at once, and notice what changes inside your sense of size. Now let everything fall quiet. No quick cuts, no rush. Picture a single ray leaving a young star on the far side of the map. It travels through thin gas and past silent halos, across voids and along filaments, through regions that will one day grow into clusters. It arrives after billions of years to strike a mirror and become a number in our hands. That number finds its place among other numbers, and together they trace a curve that says how space has stretched while the ray was in flight. We name a diameter today because of that long relay. When the hush lifts, we bring the method back into view so the awe does not float away. We used one clear ruler for the across the diameter count and spoke our edge for the Milky Way. We traced how distances are anchored, how candles and rulers overlap, and how statistics of clustering add their quiet weight. We checked sensitivities so that small shifts in parameters move the count by only small amounts. We kept the habits that make wonder sturdy: define, measure, compare, and then invite a second pass. There is a gentle paradox worth keeping. The more precisely we speak, the more room we make for feeling. Saying approximately 920,000 widths across with the present-day ruler does not crush imagination. It frames it. It gives a place for your mind to stand while it looks out. Saying approximately 276,000 with the travel time ruler does not cause conflict. It shows that questions carry the rulers they need. Here width means our working diameter for the Milky Way. When we name the ruler and the path, debate shifts from noise to substance. Let us press once more on the idea of horizons, because it teaches humility without shrinking our agency. The observable boundary is not a wall, it is a record of time. As the universe ages, more of the map becomes measurable, and observers in the far future will write larger diameters than we do today. Our method, however, will be the same. They will name their ruler, state their epoch, choose their path, and divide by a working width. The continuity of method lets generations compare meaningfully, even as data grow and tools improve. Return to the galaxy we call home and let its details settle. Our star orbits tens of thousands of light years from the center, carrying a retinue of worlds and debris. The local space is mostly empty, full of magnetic whispers and the rare clink of particles. Far away, giant molecular clouds quietly collapse in some arms and feed the birth of stars. In other arms, supernova shock waves carve shells and stir the gas. All of it is ordinary and astonishing together. Against that living background, the number we carried through the series becomes not a stunt but a shared scale. Across the sky, other islands of light carry their own stories. Some are barred spirals like ours. Some are grand design spirals with crisp arms. Some are smooth ellipticals, and some are ragged dwarfs with scattered knots of star formation. In clusters, thin arcs from gravitational lensing curve around bright cores, sketching the hidden mass that bends the paths of light. In voids, single galaxies drift like lanterns. The count across the diameter gathers all these forms into one simple comparison, without pretending that arrangement or mass are the same as size. It is healthy to ask what our habits protect us from. They protect us from mistaking pictures for measurements, from letting a dramatic rendering stand in for a definition, and from treating an analogy as if it were the thing itself. We can still use pictures and analogies as bridges, as long as we also show the planks. A coin and a country are planks. So is the checklist that repeats in your mind. Name the ruler, name the path, name the epoch, name the edge, show the division, speak the uncertainty. You can carry the practice into everyday scale questions. When someone says a device is faster or a chart shows a rise, you can ask which ruler is being used and whether the path matches the claim. When a headline quotes a distance, you can ask whether it is a present-day separation or a travel time. When a map or diagram looks persuasive, you can look for the overlap that keeps it honest. These are not tricks. They are simple forms of care learned from astronomy and usable everywhere. Let us answer 2 lingering listener questions with that care. First, if the observable sphere is centered on us, does that make us special? No. Every location has its own observable sphere centered where it stands, because light arrives where it is received. A person in a distant galaxy would draw the same circle around themselves and would reach the same order of magnitude in the count, differing only within the uncertainties of their inputs. Second, does cosmic expansion carry us apart like debris? No. Bound structures, such as galaxies and clusters, hold together by their own gravity, even as space stretches on scales larger than those bonds. Now, a practical exercise to lock the muscle memory. Take the present-day diameter you prefer from a reputable source. Take the working width for the Milky Way you find most defensible. Write both in words in your notes. Name your path across the diameter. Divide, and then write the answer in words as well. On the next line, state your 2 key assumptions in 1 sentence. That small ritual makes your number portable and reproducible. It also builds the habit of inviting checking rather than resisting it. What about disagreement between careful teams? It will appear, and that is not a failure, but a signal. If 2 present-day diameters differ by a few percent, the count will differ by a few percent. If one working width is larger by a modest factor, the count will be smaller by the same modest factor. When differences are bigger than expected, the field looks for dust, classification, selection, modeling, or calibration issues, and then it fixes them or quantifies them as uncertainty. Confidence grows not from silence, but from transparent repair. Team, bring the macro scene back for one last held breath. Imagine your eye adapting in a dark observatory dome. A slit opens, a thin beam spills onto a mirror, then through optics to a patient sensor. The sensor counts quiet arrivals one after another until a pattern forms. Later, long after the dome is closed, that pattern becomes a distance, and then a point on a curve, and then a present-day diameter. The arc from photon to phrase is long, but it is continuous. We honor it by speaking carefully when we give the final number. Our careful number is not alone. Alongside it sit cousins you met, the travel time count, the circumference count, and the variants that move the Milky Way, edge. Each exists because it answers a slightly different question with a slightly different path or ruler. Each is useful when named clearly. None is a throne. The method selects the number, not the other way around. The practice is to pick the one that fits the purpose and to say in plain words what that purpose is. Before we close, Lift your gaze one more time to the quiet overhead. Somewhere in that quiet, a supernova is unfolding. It's light on a journey that will outlast our projects and return as data for someone else. Somewhere a dwarf galaxy is falling along a filament. Somewhere a stream of stars is wrapping a halo and writing the shape of mass into the sky. Against that living map, the image of placing hundreds of thousands of Milky Way widths across the present-day diameter is not a boast. It is a way to keep our attention honest. Take with you 3 compact sentences that summarize the whole path. The observable universe is the part we can measure because light has reached us. The count across the diameter depends on the ruler, the path, the epoch, and the edge, all of which we state. The method survives new data because it is a method, not a single number. If you want a next exploration that grows from this one, try 2. First, follow the light cones. Draw how events in space-time fit inside or outside our ability to signal and to see, and watch how those cones change when you change the cosmological parameters. Second, turn to structure formation. Trace how tiny early fluctuations grow into the web we map today, and see how feedback from stars and black holes sculpts the small scale while expansion sets the large. Both routes keep the practice alive while moving into fresh territory. Thank you for walking with care through a topic that tempts shortcuts. You now have a ruler you can name, a checklist you can recite, an account you can defend in plain words. Share it forward, test it, and let it be tested. Wonder is not the opposite of rigor. When held together, they make a map that is both faithful and generous.